I am back with the second reading of this passage, and I'm going to annotate this time. And to do that, I will use my highlighters. I'm also going to be putting some of those boxes around the important terms that I need to know. So it says the standard system of measurement used by scientists around the world is known as the International System of Units, or SI. SI units are easy to use because this metric system is a decimal system of units based on a scale of multiples of 10. Each unit is 10 times larger than the next smallest unit and 1/10 the size of the next largest unit. Okay, I have a word part that I want to highlight. This is a root, the word metric. Let's go ahead and mark that. We will add that to our word parts. To measure the distance between 2 points, scientists use length. So this is a vocabulary word. We will make a flashcard for this one. And it gives us the definition in this sentence: the distance between 2 points. The size of the object being measured determines the unit that it will be measured in. For example, the length of a football field is measured in meters, whereas a pencil would be measured in centimeters. And I want to go ahead and highlight another word part, and that is centi. Okay. And I tell you what, let's go ahead and highlight the word meter as well. Excuse me. Okay, just take a look here with me at this chart. We are going to expand this chart quite a bit when we get to the graphic organizer. But let's go ahead and look at the SI base units. The quantity measured, the unit, and the symbol. That's my header row right here. The title or the topic is this one. This is the header row. Rows run left to right. Columns run up and down. So this is a row. If you are measuring the quantity of length, the basic unit in the metric system is the meter, and the symbol is just a lowercase m. If you are measuring mass in the metric system, the basic unit is the gram, and the symbol is G, lowercase. Time in the metric system, basic unit is the second, symbol is S. Electric current is measured in amperes, and the symbol is a capital A. Temperature in the metric system is measured in Kelvin. It can also be measured in Celsius, and we'll talk about that a little more later. But if you're measuring in Kelvin, you talk about degrees Kelvin. That's a capital K. The amount of substance, this is a chemistry term. It's measured in a mole, and it's exactly the way you would pronounce this word for any other use of the word. The little animal that digs up your yard, a spot on your skin is a mole, and that's the same pronunciation. But if it's the unit of measure, the symbol is MOL. And the intensity of light, this is one that you don't encounter very often unless you are a physical scientist. But this is measured in the unit called candela, and the symbol is CD, candela. Again, we're going to make a graphic with that and really dig into those units a little bit more. Mass is the amount of matter in an object. Okay, so there's another vocabulary word in bold, mass. And I immediately start looking for a definition. Sometimes it won't be there, but in this case it is. Mass is the amount of matter in an object. So there's the definition. It's connected to the concept of weight, but it's not the same thing. The mass of a basketball is outweighed by the mass of a bowling ball. They may be about the same size, but the weights are different. And let me just go ahead while we're thinking about this and put that in here. When you talk about weight, a lot of people interchange mass and weight, and that's not exactly right in science. Weight is the amount, or let's not say the amount, let's say the pull of gravity based on mass. And let me give you an example, a very practical example of this. Neil Armstrong was the first man to walk on the moon. Okay? So I'm going to draw Neil Armstrong, and then I'm going to make an exact duplicate of Neil Armstrong. So here is the same individual. But would you believe me if I told you that on Earth, Neil Armstrong weighed 180 pounds? Now, I don't know if this is true. I'm just picking a number at random. But if Neil Armstrong weighed 180 pounds on Earth, I can tell you that on the moon, when he walked on the moon, if he had stepped on a scale, it would have registered only 30 pounds. Because I know from years and years of studying science that Earth weight, or let's put it in terms of your moon weight, not your mass, but your weight, is equal to your Earth weight divided by 6. Now, you may have noticed that in one case I capitalized Earth and Moon, and in the other case I did not. I asked an astronomer this question once. I said, should I capitalize Earth, Moon, Sun? And he said, it is your decision. It's appropriate to capitalize. It's appropriate not to. So you will see me do that interchangeably. That's a grammar skill, but it's worth mentioning. Here's a math skill. Your moon weight, which for Neil Armstrong we're saying is 30 pounds, is equal to your Earth weight divided by 6. So anytime you want to know your moon weight, divide the Earth weight by 6, and that will give you the approximate weight on the moon. But here's my question to you. We know the weight's different on the Earth and the moon. Is the mass different on the Earth than it is on the moon? And the answer to that is no. Because Neil Armstrong was the same man. He left Earth 12 hours, 24 hours later. I'm not sure. It was before my time. But several hours later, he walked on the moon. But he was the same man. His clothes still fit. He didn't gain or lose actual weight or actual mass. He gained and lost weight, which is entirely dependent on the pull of gravity. Okay? So that's why they're saying, if you look at this picture of these high school kids, you have this basketball and this bowling ball, and they are approximately the same size. Just like Neil Armstrong on the Earth and on the moon. They're the same size objects. But the bowling ball has a much greater weight because it has more mass. It's more solid than the basketball. The basketball's filled with air. The bowling ball is filled with more dense material. So just a little bit on the concept of weight and mass. If you study physical science, you will get much more on that concept. Okay, I hope I didn't confuse you. If I did, please talk to your instructor. He or she can help you make more sense of this concept. The density of an object, so here is another vocabulary term, and I'm going to go ahead while I'm doing this and get this one, volume. The density of an object can be calculated based on its mass and volume. Now, density is not defined here. It tells me how to calculate density, but it doesn't really give me the definition of density. When we do our flashcards, I will give you a definition of density. Volume is, so here comes the definition, the amount of space taken up by something. Water displacement is one way to determine the volume of a solid. And I see a word part here that I want to highlight. There's a prefix, dis, D-I-S. So let's get that one. Let's also get ment, M-E-N-T, while we're doing it. Water displacement is one way to determine the volume of a solid. When an object is placed in water, the amount of water it displaces is the volume of the object. From the mass and volume of the object, its density can then be calculated. So here's a good example of water displacement. We've got what looks like, I'm not sure what that is. I thought it was a sponge, and maybe it is. We drop that piece of sponge on the water. And notice that this sponge and this block of wood are exactly the same size. We drop this block of wood on the water, and you notice that it's falling deeper below the water line. So what conclusion could we draw from that? I'm going to say that this object would you say that it's heavier or lighter? It's heavier because it displaces more water. This one, here's the amount of water that's displaced. This one is a much deeper displacement. Okay, so there's more water displaced. I can conclude that it's a denser object. And then over here, look at what happens. This is another block, but it looks like it's made of steel. This object is heaviest. Okay. I want to give you another mental picture of this concept, and I'm going to do it right here in this empty space. I'm going to draw a box, and then I'm going to make 2 copies of it. At least that's my plan. There we go. These are identical sized boxes. That's very, very, very important. They are all the same size container. I want you to think about a solid block of gold. So we're looking at a solid here. In a solid, the molecules are packed very close together, and they're usually packed in a pattern. So these atoms or molecules, usually we would say, but you could even say atoms. The most basic thing that makes up stuff is the atom. So in a solid, we have a very tightly packed arrangement of molecules. In a liquid, so think about a liquid in a container. You have something that moves around. So the molecules or the atoms are not as tightly packed, but they're still pretty well packed in there. They're sort of the middle. They're free to move around, but they're looser than the solid, but they're still contained. Okay? And in a gas, think about that basketball. I should have drawn a circle to mimic the basketball. The molecules are moving quite rapidly in a gas, so they're not as tightly packed together, and they're moving all over the place. Which of these three boxes shows the most density? Where is the density the greatest? It's going to be here. This one is the densest, and this one is the least dense. Because if I control the size of the container, and the container is exactly the same in all three situations, it's exactly the same in our other example here. In all three of these, the containers are identical. The amount of water is identical, at least originally. What we're seeing here is displacement. You're seeing the water level rise because this is so heavy. That all relates to the concept of density. Okay, the last one that we need to look at is the concept of time. What is time? Time is, there's the word is, the interval between two occurring events. And it can be measured by a stopwatch or a clock. An interval, you can think of that as another word for space. The space between two occurring events, which can be measured by a stopwatch or a clock. So, for example, let's just put this into a sort of a math problem. Let's suppose that I have two people running on a track. So here's the first person running from point A to point B on the track. I'm going to make a copy of that. So I have two identical tracks, and we're going to call this the starting point, and this is the finish line. So start and finish. So there are the 2 points, two occurring events. And let's say that the first runner takes 25 seconds to make that run. And the second runner takes 40 seconds. Now be careful with this question. I've seen a lot of students miss this. Which person is running faster? Is it the person who ran in 25 seconds, that interval, and this is called the interval, or is it the person who ran it in 40 seconds? So this space between those 2 points is called the interval. Well, it's going to be this person who is running fastest, because that person needed less time to cover that interval. So if this is a race, this is the winner. This person is faster, and this person is slower. we're sort of programmed in math to think that the higher number is always the winner or the best. But when you're talking about time, very often it's the lower number that is going to be the better choice. What I would say is that 25 is less than 40, and therefore the 25 seconds is the faster time. Okay, we will come back and look at our questions in just a second. Let me be sure that I got all of the vocabulary. There's not a huge amount in this chapter. We've got some word parts to add, and we will do that in the next segment of the lesson. We'll add our vocabulary terms.